In this lesson, we're going to look at Ampere's law and the example of a long straight wire, which we've already looked at, but this is going to be a more realistic long straight wire. It's actually going to have a thickness to it, so it has a radius r to the wire. For this example, we are going to assume that the current is uniform across the cross-sectional area of the wire. So we'll assume there's no difference in the current at little r equals 0 as opposed to capital R. When that's the case, we say that the current density, J, I divided by A, is constant. It's constant across the cross-sectional area. Well, we're going to start our analysis by actually kind of working from the outside in. We'll see that this outside result, as you can see here, is very short, because when we set up our Amperian loop outside of the wire, so, whoops, green, our Amperian loop outside of the wire, it encompasses all of the current. So I enclosed is all of it. The B field, they show us, is coming out of the paper here. Current is coming out of the paper, so the B field runs clockwise. So we get cosine of 0 degrees between the B vector and the ds vector. They both run counterclockwise. B comes out, because it's a constant by symmetry, on the Amperian loop. So there's no reason to expect this B to be different than this B to be different than this B. Anywhere on the loop, the B is constant. It comes out. Integral of ds is s. The entire Amperian loop is a circle, 2 pi r. So again, we get our long straight wire result when we are outside of the wire. Well, how about inside of the wire, when we're going to go from little r equals 0 to capital R? And you can see here I've graphed the one on R from capital R to infinity. But now let's go inside the wire, 0 to capital R. When we do that, it's a little more complicated. Still not bad, but a little more complicated. For little r equals 0 to capital R, our I enclosed is now not all of it, it's some of it. So our Amperian loop, let me zoom in here, still goes counterclockwise by convention. The current is coming out of the paper, just like it was. So the magnetic field from the enclosed current goes counterclockwise, cosine of 0. So the left-hand side of Ampere's law remains the same. So the B times 2 pi r and B times 2 pi r remains the same. And now the only thing we have to handle is the I enclosed being this shaded region. And as I have starred here, or exploded here and highlighted, we're going to use density. So the current enclosed divided by pi r squared has to equal the total current divided by the total area. It's density equals density. Current density equals current density. J is constant. And we're going to solve that for I enclosed and put that in here. So when we bring the pi r squared up, we lose the pi's. We get little r squared over capital R squared here. We lose one of the r's, and we see that the B field is linear as we go from little r equals 0 to capital R. And the only other point of interest is where these two regions intersect. At that point, the B field has to have the same value. So let's just confirm that it does. Well, when little r equals capital R, this pink capital R out to infinity, mu naught I over 2 pi capital R. So that works. Well, how about our blue equation? Well, when little r equals capital R, we lose the r, one of the r's on the bottom, and again, we get mu naught I divided by 2 pi r, so our equations are consistent. Our intersection points match as well. So I'm going to take some of my additional checks and comments off of this so that if you need to annotate something you did not, you can pause the screen here and do that. and we will move on.